Traffic Optimization by Sanjana Kadiala and Florentina Sahaya. Okay, so to do this entire thing, we have to start off by looking at the traffic flow function, which is the main concept of all of this. Q equals PV. In this, Q of x of comma t is represents traffic flow at position x and time t, measured in cars per unit time. P of x of t represents traffic density, which is the number of cars per unit distance, and V of x of t represents velocity, which is the speed of the cars in distance per unit time. So these are just like the main variables that we need to get to know. Okay, so now this is the flow conservation equation and the continuity equation. In this, we're setting partial derivatives. The first term represents the change in traffic density over time, and the second term represents how traffic flow changes along the road. And we're adding these two together and equaling 0 to try to take in consideration these two main variables. So to do this, we need to also move on to getting the velocity density relationship. V of p equals V max times 1 minus p over p max. V max is the maximum vehicle speed under the free flow conditions. P max is the jam density, the maximum possible density before traffic comes to a complete stop. As p approaches p max, velocity approaches 0. We're going to substitute this all into the fundamental flow equation Q equals PV to obtain the equation that we have below. Okay, so now we have to actually do the optimization portion where we're finding W, which is the total time that we need to wait, and we're trying to minimize W. So this is the equation that we have, in which I represents each road leading to the intersection, T is the total cycle time, which is sum of all the lights durations. Mainly we're going to do green and red for this one. Pi is the traffic density for the road I at time t, Vi is the velocity on road I at time t, and the end goal is just to minimize W. Okay, so we have to look at the constraints. Cycle time constraint is that the sum of the green and the red have to equal the total time C. And so now moving on to the capacity constraint, Qi times Gi has to be less than or equal to Li, which is basically saying the vehicles passing through the intersection during the green time must be within the lane capacity Li. So Qi is the traffic flow rate for road I, and Li is the representative of the maximum number of vehicles that can pass. So we also need to look at flow conservation constraint, which is the amount of vehicles in, so Q in has to equal Q out. That's just making sure it's balanced. So now we're solving using the Lagrange multipliers, and this is the equation right there. And the first term, W, is the total waiting time, like I said earlier, and the second term is multiplied by lambda 1, which enforces the cycle time constraint. The third term multiplied by lambda 2 enforces the capacity constraint, and the fourth term multiplied by lambda 3 enforces the flow conservation constant. And then so now we're finding optimal solutions. So we're gonna find the optimal green light and red light durations. So to do this, we differentiate the Lagrangian with respect to each variable and set the derivatives equal to 0. Solving these equations simultaneously gives us the optimal traffic light timings and that minimize congestion. So now we're just going to apply this to the real world. So I'll see you there. Oh my god, I hate driving. Can't the guy sitting right behind the desk who fiddles the green light just turn it on already? How long does it take? This guy should be fired. Bro, move it! Let's look into the math that we do for this particular intersection and how we can optimize it. So let's set some variables. So the max velocity is 30 miles per second, and the max density is 0.5 cars per meter, and the cycle time is 90 seconds. So let's go to the lane capacity. Li equals 50 cars per cycle in each direction. Initial density of road 1 would be 0.2 cars per meter, and road 2 is 0.35 cars per meter. So we set those variables. Now we can do the function out, which is V of p equals V max 1 minus p over p max. And for road 1, V1 equals 30x in brackets 1 minus 0.2 over 0.5 equals 30 times 1 minus 0.4 equals, let's solve that out, we get 1.8 meters per second. And then we solve the second one out and get 9 meters per second. Okay, so let's plug this into Q equals PeV, our original function again. Okay, so let's just simplify that out. Q1 equals 0.2 x 18, 3.6 cars per second for the Q1, and then for Q2 it's 3.15 cars per second. Okay, so now that we have the base stuff set with the traffic density flow function and all that, and we have that set, we can start talking about minimizing the total wait time by setting W, which is just the total wait time variable that we assign to our function that we set, and then our total cycle time constraint is going to be G1 plus G2 plus R1 plus R2, which is just all the light signals that possible, equals C, and we're setting C equals 90. And we're going to assume that the red time is equal, and we're assuming it's 15. Okay, and then now onto the capacity constraint. Qi times Gi has to be less than or equal to Li. So basically, we're setting Li to 50, and then for road 1 it would be 3.6 times G1 has to be less than or equal to 50, and for road 2 it would be 3.15 times G2 is less than or equal to 50. And then for the flow conservation, it would be Q1 plus Q2 equals Q out, just to make sure that there's no additional inputs or too much output to keep it balanced. Now we're going to try solving this using the Lagrange multiplier. So we're going to define the Lagrange multiplier function as I'm writing it down right here, and we're going to substitute all our variables in. And then now I'll take all the partial derivatives as I set them equal to 0. So we'll just do that really quickly. And so this will help us really isolate each variable out so that we can find what G1 and G2 is on specifically. Okay, so now that we set them equal to 0, we can basically create our capacity constraints, which is 50 over 3.6 for G1, which is 13.89 seconds, and 50 over 3.15 for G2, which is 15.87 seconds. And then the total cycle time constraints. So because of this, we get 29.76. And so the remaining time for other roads is 30.24, just 60 minus 29.76, which could be split equally between the two roads. So overall, we get these results. So for road 1, green equals 13.89 and red equals 15, and for the road 2, green equals 15.87 and red equals 15 seconds. That's the overall results.